There's a deep connection between electricity and magnetism. Whenever electricity or charges are moving, that triggers a magnetic field in the vicinity of those moving charges. In the case of a long straight wire, it creates a magnetic field around the wire, kind of circular around the wire. We know that the strength of the magnetic field follows the equation magnetic field B equals the magnetic field constant. We're going to call it mu times current over 2 pi r. There's a cool calculus proof about why it's 2 pi r, why it's the circumference of the circle. You'll get to that eventually in calculus, but for now just mu I over 2 pi r. That equation will give you the size of the magnetic field. Then we'll use left-hand rule or right-hand rule to get the actual direction. If the current's in a long straight wire, the left-hand, right-hand rule is the hitchhiker hand configuration. Your thumb matches the current. When you get your thumb pointed in the right direction, then your fingers curl in the direction of the magnetic field. For the numbers I made up, we've got 4 amps moving through a wire. We'll deal with the direction in a sec, and we're curious about the magnetic field 10 centimeters away from the wire. It doesn't say anything about it not being in air. So for the case of air, our magnetic field constant is 4 pi times 10 to the negative 7. It's got funny units. We can write it as Tesla meters per amp. For the given numbers, the B field's going to be that constant, 4 pi times 10 to the negative 7. The current given in the question was 4 amps. And divide by 2 pi. The R we need to put in meters. The R was 10 centimeters, so 0.1 meters. When you crank that out, we get some nice canceling. The 4 pi cancels with the 2 pi, so we've got a 2 on the numerator. 2 times 4 divided by 0.1, and we've got a 10 to the negative 7 to add to that. We end up with the number 8, and the decimal gets shifted 1 spot, so it's 8 times 10 to the negative 6 Teslas. That takes care of the number part. To deal with the direction, let's doodle a little picture. It says negative flow is moving away from you. Our convention to show vectors pointing away, the away vector is an X. Since it says negative flow, use your left hand, make a hitchhiker shape, point your left thumb so it's away from you. When you do that, you'll notice that your fingers are curling in the counterclockwise direction. The question was a little bit vague, so the direction depends on where you are relative to the wire. If you're above the wire, then the magnetic field will be pointing to the left. If you're below the wire, the magnetic field will be pointed to the right, and then of course up on the right, down on the left, or we could just say counterclockwise around the wire.